When a whale completes its life at the ocean surface, something begins that most people never consider. The body, which may weigh anywhere from 10 to 100 tons depending on the species, begins to sink. It descends through the sunlit zone, through the twilight zone, through the midnight zone, through layers of water that grow progressively colder and darker and more pressurized. The descent takes hours, sometimes days, depending on the depth of the seafloor below and the gases building inside the carcass. Eventually it settles onto the bottom at 1,000 meters, or 2,000 or 3,000, landing with enough force to press into the soft sediment, sending up a slow cloud of debris that drifts outward and then resettles. And then the seafloor, which a moment ago was as close to empty as any place on Earth can be, begins to fill with life. What happens after a whale reaches the ocean floor is one of the most elaborate ecological processes in the deep sea. A single large carcass can sustain a community of hundreds of species for decades, sometimes longer than a century. It passes through stages, each one populated by a completely different cast of organisms, each one unlocking resources that the previous stage made available. It functions in the barren economy of the deep ocean, like a city that appears overnight in an empty desert and slowly, methodically, uses everything the city was built from. Marine biologists call this a whale fall, and the organisms that make it possible include some of the most specialized creatures in the ocean, including one that recently began disappearing in ways that have researchers genuinely concerned. The first stage begins within hours of the carcass settling. The deep ocean floor is, by the standards of the surface world, extraordinarily sparse. Food descends from above as what oceanographers call marine snow. A slow, thin rain of organic particles, fecal matter, and the remains of tiny organisms that drift downward from the productive surface layer. In most areas of the deep sea floor, this rain delivers only enough energy to support a thin, widely spaced community of animals. Sea cucumbers moving slowly across the sediment, brittle stars with arms extended into the water to catch passing particles, the occasional deep-sea fish patrolling a territory of several square kilometers. A whale carcass is the opposite of marine snow. It is an enormous, concentrated pulse of organic energy, the equivalent of thousands of years of background food delivery, arriving all at once in one location. The largest whales contain 100,000 kilograms of soft tissue. In the context of the deep sea floor, this is an almost incomprehensible surplus. Within hours, the animals that sense it begin to arrive. Hagfish, long, soft-bodied animals that navigate by chemical detection, arrive first, burrowing into the soft tissue. Sleeper sharks circle in. Mobile crustaceans gather from across the surrounding seafloor. This first stage, which researchers call the mobile scavenger stage, can strip the soft tissue from a large whale carcass in a matter of months. The animals feeding here are not specialists. They are generalists of the deep floor, opportunists that follow chemical signals through the water and find the carcass by smell across distances of kilometers. What they leave behind, the skeleton, still rich with fats and oils embedded deep in the bones, is the foundation for everything that follows. The second stage is slower and more structured. Once the mobile scavengers have processed the soft tissue, a different community moves in. This is the enrichment opportunist stage. Smaller organisms, polychaete worms, crustaceans, mollusks, colonize the bones and surrounding sediment, feeding on the remaining organic material and on bacterial films that have begun to grow across the surface of the carcass. The species diversity at this stage is much higher than during the first. A single whale skeleton in this phase has been found to host more than 200 species of invertebrates simultaneously, many of them found nowhere else in the surrounding seafloor. The whale fall has become, in the space of a few months, the most species-rich location for hundreds of square kilometers in any direction. This stage can last for years. The bacterial films cycling across the bone surface and the organic material settling into the surrounding sediment support a dense, layered community that processes the carcass from the outside. But the real energy, the dense lipid reserves packed into the interior of the whale's bones, is still locked away, inaccessible to most of the organisms feeding at the surface. Unlocking it requires a specialist, and the specialist is one of the most unusual animals in the deep ocean. Osedax is a worm, though calling it a worm in the casual sense understates how strange it is. It has no mouth. It has no stomach. It has no digestive system in any conventional sense. What it has instead is a network of branching root-like structures that it pushes directly into the surface of whalebone, secreting an acid that dissolves the hard outer layer and allowing the roots to penetrate into the fat-rich interior. Inside those roots, dense colonies of symbiotic bacteria live permanently, bacteria that digest the fats and oils the roots absorb and convert them into nutrients that the worm absorbs directly. The worm is, in functional terms, a biological drilling system connected to an internal fermentation tank. It does not eat the bone in any way we would recognize as eating. It dissolves its way in and then outsources the digestion to the microbes living in its own tissue. Osedax was not discovered until 2002, when researchers from the Monterey Bay Aquarium Research Institute lowered a whale carcass to the floor of Monterey Bay and returned months later to find it covered in what looked like flowers, clusters of translucent, feathery plumes extending from the bone surface into the water above. The plumes were the respiratory structures of the worms. The roots were invisible, buried in the bone. Nobody had known the animal existed before that day, despite the fact that it is likely one of the most numerous specialized organisms on the deep sea floor. The female Osedax is the one with the roots, the plumes, and the bacterial colonies. The males are microscopic, tiny, simplified animals that live inside a protective tube on the female's body with one function: reproduction. A single female may carry dozens of males. The males never develop full anatomy. They retain the juvenile form permanently and exist entirely as reproductive units hosted by a female that is herself a specialist organism hosted by a whalebone. This is, even by deep-sea standards, a remarkable arrangement. When Osedax finishes with a whalebone, when the roots have processed enough of the fat content that the inner bone becomes depleted, the worms move on. Their larvae are released into the water column and drift, sometimes for months, until they sense the chemical signature of a new whale fall and settle. The distance they can travel between whale falls has been estimated at hundreds of kilometers. They are, in effect, island hoppers, moving between temporary habitats that appear unpredictably across a vast and mostly empty seafloor. The third stage of a whale fall is the longest and, in some ways, the most extraordinary. When Osedax and the other bone-processing organisms have worked through the accessible fat content, the bacteria that remain shift to a different metabolic strategy. They begin breaking down the deepest lipid reserves inside the bone structure itself, and in doing so, they release hydrogen sulfide, the same compound that powers the chemosynthetic food webs around hydrothermal vents. The whalebones begin, in a very literal sense, to behave like a small, slow vent. Hydrogen sulfide diffuses out of the skeleton and into the surrounding sediment and water. And the organisms that specialize in hydrogen sulfide-based chemistry, the same families of bacteria, clams, mussels, and tube worms found at hydrothermal vents, arrive and establish themselves around the bones. This stage is called the sulfophilic stage, and it can last for decades. A blue whale skeleton, which contains extraordinary quantities of bone lipid, may sustain sulfophilic community activity for 80 to 100 years after the carcass first settled. The bones become encrusted with white bacterial mats, surrounded by clusters of specialized bivalves, colonized by organisms that exist nowhere else on the seafloor that is not chemically enriched. The whale fall, which began as a pulse of organic energy, has become a persistent chemical habitat. A slow-release system that sustains a specialized community for a span of time longer than most human lifetimes. The total species count across all 3 stages of a single large whale fall can reach 400 or more. Many of these species are found only at whale falls, organisms so specialized for the chemistry and physical structure of whalebone that they exist nowhere else in the deep ocean. Some of them appear to use whale falls as stepping stones, dispersing larvae between carcasses across ocean basins, maintaining populations across habitats that are separated by hundreds of kilometers of otherwise unsuitable seafloor. In 2024, researchers monitoring a whale fall experiment in Barkley Canyon, off the coast of British Columbia, found something unexpected. The Osedax worms were not there. The experiment had placed whale bones on the seafloor in a region that falls within a naturally occurring low oxygen zone, an oxygen minimum layer that sits at depth in parts of the Northeast Pacific. Researchers expected the whale fall to proceed through its normal stages. What they found instead was that the key specialist, the worm that unlocks the bone lipids and triggers the transition to the sulfophilic stage, was absent. The bones were sitting on the seafloor with the bacterial films of the enrichment stage, but without Osedax, the progression to the deeper stages had stalled. The likely reason is the expansion of the oxygen minimum zone. As ocean temperatures rise, the low oxygen layer in the Northeast Pacific has been expanding, growing larger in area and shallower in depth. Osedax larvae drifting in the water column cannot settle and survive in water with insufficient oxygen. The chemical signal of the whale bones may be reaching them, but the environment they would need to settle into has become inhospitable. The stepping stones between whale falls are not disappearing. The worms that use them are finding the water between the stones increasingly difficult to cross. Researchers who published the findings described the situation with careful scientific language, but the implication was clear. If Osedax cannot reach whale falls in a growing portion of the Northeast Pacific, the full succession of the whale fall ecosystem, including the sulfophilic stage that can sustain hundreds of species for a century, may not complete. The organisms that depend on that stage have nowhere else to go. The whale fall is, in the economy of the deep ocean, something like a gift that keeps redistributing itself. The whale spends its life at the surface, consuming enormous quantities of krill and small fish, accumulating in its body an extraordinary concentration of organic energy. When it completes its life and descends, that energy does not disappear. It transfers, first to the mobile scavengers, then to the enrichment community, then to Osedax and the bone processors, then to the sulfophilic community. Across a succession of organisms that collectively extract nearly everything of value from the carcass over a period of decades, leaving behind at the end only a dispersed mineral substrate that slowly becomes part of the sediment. The energy that the whale gathered at the surface over decades of feeding is distributed across the deep seafloor across a century of ecological succession. Nothing is wasted. The community is extraordinarily efficient. This efficiency is the product of millions of years of co-evolution between whale falls and the organisms specialized to process them. Osedax did not appear recently. Its fossil record extends back at least 30 million years to the early Oligocene, when baleen whales first began reaching the sizes that make whale falls ecologically significant. The stepping stone network of whale fall habitats across ocean basins has been operating with the same basic cast of specialists for tens of millions of years. What took tens of millions of years to assemble can be disrupted on the timescale of decades. The expanding oxygen minimum zone in the Northeast Pacific is a measurable phenomenon. The absence of Osedax from Barkley Canyon is a measurable observation. The connection between them is not certain. The researchers are careful to say so, but it is the most plausible explanation available, and the preliminary data from other sites is consistent with it. The whale fall ecosystem is one of the more complete expressions of how the deep ocean makes use of every resource available to it. The fact that one of its key organisms may now be struggling to reach its habitat is not a dramatic story in the way that surface ocean events can be dramatic. It is slow, invisible, and happening at depths that almost no one will ever visit, which is perhaps the most accurate summary of how the deep ocean changes. Quietly, in the dark, in ways that take years to notice and longer to understand.